So how would we calculate the grams of magnesium phosphate that contain 25 grams of magnesium? Well, we have to find the proportion of magnesium in the magnesium phosphate, and we do that with atomic mass. So here are the masses. We have 3 magnesiums at 24.3. That's 72.9 grams of magnesium contributing to the formula weight. We have 2 phosphorus atoms at 31 each. That's 62. And we have 8 oxygen atoms at 16 for 128. So adding them all up, we get a formula weight of 262.9 grams per mole. Grams per mole. So we can make a proportion now out of that using the 72.9 of the magnesium and the 262.9 total to get a proportion of magnesium to the total mass of magnesium phosphate. And we can write that proportion in 2 different ways. Here are the 2 ways we can express this proportion, you see. Either 72.9 grams of magnesium per 262.9 grams of magnesium phosphate, or the inverse of that. Now, one of these is going to be the useful one, the conversion factor we need to convert from 25 grams of magnesium to grams of magnesium phosphate. In other words, we want to cancel grams of magnesium and we want to end up with grams of magnesium phosphate. So which conversion factor, this one or this one? They're both equivalent to each other, but which one is going to be the useful one in making that conversion? So here's how we set up the problem to solve for grams of magnesium phosphate. Notice that we have grams of magnesium and we want to cancel that out and be left with grams of magnesium phosphate. So only this relationship will allow you to do that. With the magnesium phosphate, what we want, our target, in other words, in the numerator, and what is going to be canceled out, the grams of magnesium in the denominator. So we have grams of magnesium in the denominator times units of grams of magnesium. Those will cancel out. And to get the answer, then we just multiply 25 times 262.9 divided by 72.9. And that leaves 90.2 grams of magnesium phosphate as the answer. Well, here is a similar problem with another wrinkle in it, another step, if you will. Otherwise, the first step is exactly the same to what we just did. An ore is 6.2% in calcium phosphate. How many kilograms of ore would contain 100 grams of calcium? So really in this one, we've got 2 steps to do. First, start with the grams of calcium and go to grams of calcium phosphate, just like we did in the last problem. But then, to use the percentage, 6.2% in calcium phosphate, to go from grams of calcium phosphate to grams of ore. So let's set this problem up much like we did the other one. We have 3 calciums at 40, that's 120.3, 2 phosphorus at 31, 62, and 8 oxygen at 16, that's 128. So the formula weight of this is 310.3, and the proportion is going to be the calcium 120 to the total 310. So what I'm going to do is take my 100 grams of starting information about calcium, and then I'm going to use the proportion 310.3 grams of calcium phosphate in the numerator and 120.3 grams of calcium in the denominator, so that my grams of calcium cancel out and I'm left with grams of calcium phosphate. Very important point here. If you get sloppy about your units, if you just put 310 grams divided by 120 grams, you won't have any map, you won't have any guidelines as to how to do the problem. And it opens the way to getting the problem wrong. Take a little time, be complete in the units that you use, and let the units guide you to the answer. As I say, you might save a fraction of the amount of time not making the units complete, but the downside is you'll be opening the door to all kinds of error. You'll be throwing away the map, and you'll be guessing as to which number to put on top and which one to put on the bottom. Complete units are very important for success in this course. Okay, if you multiply your 100 by 310, divide it by 120, we get 258 grams of calcium phosphate. But the question doesn't stop there. It says we want the grams of ore that contain this amount of calcium phosphate, so that this amount of calcium phosphate will contain 100 grams of calcium. So this is halfway done. How do we go from grams of calcium phosphate to grams of ore? Well, that's the 6.2%, isn't it? And being able to translate 6.2% into useful units. Well, what is percent? It means per 100. And if it's 6.2%, the ore is 6.2% in calcium phosphate. That means that for every 100 grams of ore, you have 6.2 grams of calcium phosphate. So this is the ratio, either 100 divided by 6.2, or it'll be 6.2 divided by 100. And you want the ratio that's going to cancel out grams of calcium phosphate and leave you with grams of ore. So that means you have to put the grams of ore, 100 grams of ore in the numerator, 6.2 grams of calcium phosphate in the denominator. Grams of calcium phosphate will cancel, and when you multiply it out, you'll get something like 4160 grams of ore. But notice again, the question is asking for kilograms of ore, so you're going to have to divide by 1,000 and then round off to 4.2 kilograms. Now here's another kind of skill you need from Chapter 3 is being able to determine what an empirical formula is from the mass percentage or the makeup by mass of a compound. In other words, given the mass of different elements in a compound, being able to convert that into a formula. First of all, what's a formula mean? If you are talking about, for example, H2O, remember you're talking about two atoms of hydrogen bonded to an atom of oxygen. So the 2-to-1 relationship there is a particle relationship. 2 atoms of hydrogen for 1 atom of oxygen. Or it could be 12 atoms of hydrogen to 6 atoms of oxygen, if we're talking about more than one molecule. It could be 2,000 atoms of hydrogen to 1,000 atoms of oxygen, if we're talking about 1,000 molecules of water. Or if we're talking about a mole of water molecules, then we're dealing with 2 moles of hydrogen atoms and 1 mole of oxygen atoms. The formula itself is a relationship in particle numbers, and because moles is a unit of particle numbers, a very large number of particles, that whole number relationship works for moles too. So you don't see the whole number relationship in grams. You can't get it directly from grams, but if you convert the gram makeup of a compound into moles for each one of those elements, a whole number relationship will emerge from that information. So let's do this. Here we have 18 grams of hydrocarbon. It is just carbon and hydrogen. It contains 18 grams total, and then of that 18, 3.6 grams are grams of hydrogen. So we know the mass of one element, and we know the mass of the total, and we know there are just two elements. So if we subtract our 3.6, 14.4, won't it, grams of carbon. This is grams total. This is grams of hydrogen. So 14.4 grams of carbon. Now, as I said, the whole number relationship in the formula does not emerge from grams, but it does emerge from moles. So what we're going to do is convert the grams of hydrogen into moles of hydrogen and the grams of carbon into moles of carbon. Let's do that. 3.6 grams of hydrogen divided by 1 gram of hydrogen per 1 mole of hydrogen, right? And so that's simple, 3.6 moles of hydrogen. How about our carbon? Well, carbon's going to be 14.4 grams of carbon. That's 12 grams of carbon per 1 mole of carbon. So it's 14.4 divided by 12 equals 1.2 moles of carbon. So now we've converted each one of these elements, carbon and hydrogen, into moles. And from this, we should see a whole number relationship emerge. And you can practically do this just squinting at it. 1.2, 3.6. Hey, that's going to be a 1 to 3 relationship. But the official way to do it, sometimes it's not as obvious, is to take the smallest number of moles and divide every element's number of moles by the smallest one, or the smaller one in this case. So we're going to divide this by 1.2, we're going to divide this by 1.2, and we will have C1H3. Now that's what we call the empirical formula. And it's the simplest whole number relationship between the elements in the formula. It may not be, and in this case is not, the molecular formula. It's not the same. Empirical means by experimentation, via experiment. This is the formula that emerges when you do an experiment to determine the grams of hydrogen and carbon in a compound. We'll show you how to do that in a couple of slides, but it is the simplest whole number relationship, the relationship that emerges just from finding the mass of each of the elements and converting them to moles. But if you want the molecular formula, you also have to know the molar mass. In this case, the molar mass is 30. Here's how you find the molar mass. You find the molar mass of your empirical formula. That's pretty easy. Carbon is 12. Hydrogen is 3. You have 3 hydrogen plus 12. So the formula weight of this empirical formula is 15 grams per mole. And if you divide that into the actual molar mass of the compound, you're going to get a multiplier. And 30 divided by 15 provides us a multiplier of 2. So what I'm going to do is multiply every subscript by 2 to give us, it will no longer be the simplest whole number relationship, but it'll have the correct molar mass. So I'm going to have 2 carbon, and I'm going to have 6 hydrogen, and it's going to have a molar mass of 30, and yet the carbon and hydrogen are still in the relationship of 1 to 3. Okay? So the empirical formula, just to recap, find the grams of each element, convert to moles, divide through by the smallest number of moles, and what will emerge is the whole number relationship. If you want the actual molecular formula of the compound instead of the empirical formula, you will need the molar mass. Then find the molar mass of the empirical formula, divide it into the actual molar mass, and you'll have a multiplier. And if you multiply each subscript by the multiplier, you'll end up with the actual molecular formula. Okay, let's start one. Let's try one that you can do, and then you can check your work, all right? Here I have a substance, a compound. The mass percent is 54.6 grams of carbon per 100 grams of compound, 9 grams of hydrogen per 100 grams of compound, and 36.4 grams of oxygen. What I want you to do is pause the video, try and do this. The molar mass of this compound is 88. So can you come up with the molecular formula? Go ahead, pause your video, try it, and then continue, and I'll show you how you do it, and you can compare, okay? Go ahead, pause your video. Of course, we need to first convert each of these masses into moles. So we'll divide the grams of carbon by 12 grams per 1 mole. Moles of carbon. And 9 moles of hydrogen, and 2.275 moles of oxygen. We divide each of these by the smallest number of moles, which is 2.275. So this is 2.275. This is 2.275. And this is divided by 2.275. Dividing this out, I'll end up with a 2 for the carbon. I'll end up with a 3.95, which we're going to round up to 4 for the hydrogen. And for oxygen, we'll have 1. So the empirical formula is C2H4O. Find the molar mass of this, 44. So that's the molar mass of the empirical formula. If we divide that into the 88, 88 divided by 44 gives us a multiplier of 2. That's our multiplier. So what we're going to do is multiply every subscript by 2. And when we do that, we'll get C4H8O2. And that should have a molar mass of 88 grams per mole. Did you get it right? I hope so. Let's see how empirical formula determination is used in a research laboratory. Suppose you're working to synthesize a compound containing carbon, hydrogen, and oxygen. Well, you run the reaction, you collect and purify your sample, but now you have to prove that you synthesized or created what you set out to create. You just can't assume that the correct compound has been made or that you haven't isolated a byproduct. So you take the purified sample, you send it to an analytical laboratory where they run an elemental analysis of the sample. And here's how that works. They put your sample in a furnace and they stream pure oxygen gas over it and they ignite it. Now, any carbon in the sample combusts to form carbon dioxide gas, and any hydrogen in the sample combusts to form water. So the oxygen stream now carries carbon dioxide and water into two U-tubes. The first U-tube is filled with a water absorber. And if you weigh the U-tube before the reaction and after the reaction, the difference is the weight of water created by the combustion. It gains weight. The water's absorbed. So now you know the grams of water that have been created by the combustion of your compound. The stream continues into another U-tube with a carbon dioxide absorber. Again, if you weigh the U-tube before and after, the difference in weight will be the grams of carbon dioxide formed in the combustion. So how now do you take those grams of water and grams of carbon dioxide and find the grams of oxygen that have been consumed? Well, here's how it works. Suppose that 2.445 grams of carbon dioxide have been formed when your compound burns. Well, the ratio of carbon to carbon dioxide in grams is given as you would figure out the percent carbon in carbon dioxide. In other words, the ratio of the 12 grams of carbon for every 44 grams of carbon dioxide. So you can make this ratio 12 grams of carbon per 44 grams of carbon dioxide. And if you multiply the grams of carbon dioxide produced by this ratio, grams of carbon dioxide will cancel and leave you with grams of carbon. So the amount of carbon carried by the carbon dioxide is 0.6668 grams of carbon. We do the same kind of calculation with the water to figure out the grams of hydrogen. In other words, 0.6003 grams of water were produced in the combustion. There are 2 grams of hydrogen for every 18 grams of water. Multiply by this ratio, grams of H2O will cancel and leave us with grams of hydrogen. But what about the oxygen? We can't analyze the carbon dioxide and water per se for the oxygen. We're adding oxygen at this point, right? We could do it with the carbon and hydrogen because the only source of carbon and hydrogen was from the sample. We can't do the calculation we did for these two with the oxygen because we're adding oxygen. But we can do it by subtraction. In other words, if I know the total weight of the compound before I start out, 0.8233, all right, that's everything, carbon, hydrogen, and oxygen. And now if I subtract the grams of carbon and I subtract the grams of hydrogen, what's left has to be the grams of oxygen right here. So now I have grams of carbon, grams of hydrogen, grams of oxygen in my sample, and I can do the usual calculation to determine empirical formula. So what we're going to do now is convert our grams of carbon, grams of hydrogen, and grams of oxygen into moles of each one of those, just as we've done for the previous empirical formula determinations. If I take my grams of carbon, 1 mole of carbon is 12 grams of carbon. Grams of carbon cancel out. Now I have 0.05557 moles of carbon. Hydrogen is 0.0667 moles of hydrogen, and the oxygen is 0.005613 moles of oxygen. Now I take the smallest number of all those, which is the oxygen, 0.005613. This gets divided by 0.0056139.9. 9.9. Hydrogen divided by 0.005613, and that's going to give me 11.8. And my oxygen, of course, divided by itself, is going to give me 1. So 9.9 rounds off very nicely to 10. 11.8 rounds off very nicely to 12. And 1, there's my ratio. Empirical formula C10, H12, O. And hopefully the compound you set out to make has that empirical formula. And if it does, you've got a little bit of evidence there that you've succeeded in creating the compound you set out to make. Balanced equations become very important to chemists because they explain or they show what happens in the actual reaction. Methane, CH4 plus oxygen, burns to form carbon dioxide and water. Let's balance that equation. Well, to balance an equation like this, we always balance the simplest molecule last. The one that's the simplest, that only has like one element in it. This is simplest because it only contains oxygen. This contains carbon and hydrogen, or this is carbon and oxygen. So the least complex molecule is the O2, and that's what gets balanced last. So here we go. Here's one carbon, here's one carbon, so carbon seemingly is balanced. 4 hydrogen on this side, 2 hydrogen on this side. So we don't have enough hydrogen on the product side. The way we increase the number of hydrogens is by adding a coefficient in front of the water, and that coefficient is going to have to be a 2. Then we have 2 times 2, or 4 atoms of hydrogen, and that balances with 4 atoms of hydrogen on the reagent side. So carbon is now balanced, 1 and 1. Hydrogen is balanced, 4 and 4. The only thing that is not balanced is the oxygen. Carbon dioxide has 2 atoms of oxygen. The water now has 2 atoms of oxygen. That's 4 atoms total. We only have 2 over here. So we're going to balance this equation by putting a 2 in front of the oxygen. Okay, here's another one. KClO3 yields KCl plus O2. So again, oxygen is the least complex molecule. With only oxygen, we balance that last. So we have 1 potassium on both sides. We have 1 chlorine on both sides. But we have 3 oxygen on one side and 2 on the other side. So oxygen is not balanced. To balance an equation like this, it is perfectly okay to temporarily use an improper fraction. If I multiplied the oxygen by 3 halves, just as a temporary fix to get us to the balanced equation, I would have now a balanced number of oxygen on both sides. 3 halves times 2 is 3 oxygen, and that's balanced with 3 oxygen on the reagent side. But I can't leave it like this. I can't leave it as an improper fraction. So what I'm going to do is take this entire equation and multiply it by the denominator, the 2, in the improper fraction denominator. I'm going to multiply every term by 2, both reagent side and product side. So when I'm done, I'll have 2 KClO3, and I'll have 2 KCl, and I'll have 3 O2. And this is still balanced. 2 potassium on both sides, 2 chlorines on both sides, and 6 oxygen on both sides. Let's balance this one now. We have sodium phosphate and calcium hydroxide forming calcium phosphate and sodium hydroxide. Well, now you see that most of these have multiple atoms in them, and therefore we can't use the rule of balancing the simplest last. But we can just jump in and start balancing. Arbitrarily, we can choose any atom we want. I'm going to start with sodium because it's first. I have 3 sodium on this side. So I'm going to put 3 sodium over here, and now sodium is balanced. Now, the phosphate, I have 1 phosphate on this side. But I have 2 phosphate on this side, and it's very helpful to look at the polyatomic ions as units, like the hydroxide unit and the phosphate unit, and balance those units rather than individually balance phosphorus and oxygen separately. So we have 1 phosphate on the reagent side, 2 phosphates on the product side. That's not going to do. I'm going to have to balance the phosphate by putting a 2 in front of the sodium phosphate. But that now changes the number of sodium I have from 3 to 6. 2 times 3 is now 6 sodium. So I have to go over to my product side and fix it, and I have to put a 6 in front of the NaOH, not a 3. Now my sodium is balanced on both sides. And the phosphate is balanced on both sides. Now let's look at the calcium. We have 1 calcium over on the left side, 3 calcium on the product side. I'm going to put a 3 right here. And now I have 3 calcium on both sides. And I have 6 hydroxide. And there it is. I already have 6 hydroxide on the product side. This is now a balanced equation. Now, another question, what kind of relationship does a balanced equation provide? We can say that this balanced equation represents 2 formula units of sodium phosphate reacting with 3 formula units of calcium hydroxide to form 1 formula unit of calcium phosphate and 6 of sodium hydroxide. We can also say that 2 moles of sodium phosphate will react with 3 moles of calcium hydroxide to form 1 mole of calcium phosphate and 6 moles of sodium hydroxide.